Okay, so we're back with the second part of confidence intervals, and I just wanted to say one thing about confidence intervals before we jump into the second half of this section. You can use your calculator to compute a confidence interval on the AP Stats exam, but there's a risk. If you just give the calculator answer with no work, you'll either get full credit for the do step if it's correct, or no credit if it's wrong. If you opt for the calculator only method, be sure to complete the other three steps and give the interval in the do step. Okay. So basically what I'm talking about here is if we look back at our example that we did at the end of the last video, we did our four-step process here. This whole do step, we can basically punch everything into the calculator and just report the interval. But if there's no work, if the interval's wrong, you won't get credit for the do step. If the interval's right, you will. So you're kind of playing a risk there. There's like not going to be any partial credit because you didn't show any work. So it's usually good to write down the p hat and then the setup for calculating your confidence interval. Okay. All right. So let's jump into part two here, where we're going to talk about factors that affect the margin of error. So in general, we prefer narrow confidence intervals. In other words, the intervals with the smallest margin of error. So to reduce the error in confidence intervals, we can look at two different factors: the size of the sample and the confidence level. And so here's how we decrease the margin of error. In general, the margin of error gets smaller when the confidence level decreases. So you're going to have to be willing to accept a smaller capture rate. So instead of a 99%, maybe you go with a 95 or a 90 or an 80% confidence interval. But then you lose a level of confidence. Now, the other way to do it is to increase the sample size. So if you have a larger sample, that's going to reduce the margin of error for the same confidence level. So for example, if I am constructing a 95% confidence interval, but I double or triple or quadruple my sample size, that too will decrease the margin of error. The drawback to that one, however, is that there may be limits and constraints with getting larger sample sizes. Um, some of them may be expenses in conducting the sample, and also you want to be careful about the 10% condition. So let's look at some examples here. In the cell phone example, we were 95% confident that the interval from zero point 0.2 to 0.261 captured the true proportion of all cell phone users who would admit to walking into something or someone while talking on their cell phone. That interval was based on a sample of 738 cell phone users. So if we want to know what would happen to the width of the interval if the confidence level were increased to 99%. So in general, because we increased the confidence level, the confidence interval would end up being wider. It's basically doing the opposite of what we did here. This is to decrease the margin of error, you're going to have the confidence level decrease. Well, in this case, we increased the confidence level. Okay, so the confidence interval would be wider because increasing the confidence level from 95% to 99% increases the margin of error. Okay. How would the width of the confidence interval based on a sample of 1500 compared to the original 95% confidence interval, assuming the same proportion, assuming the sample proportion remained the same? So in this case, we've increased the sample size, so the width would be narrower. So the confidence interval would be narrower because increasing the sample size from 738 to 1500 decreases the margin of error when everything else stays the same. Okay? All right. So, but we do have to be careful about is that the fact that margin of error does not account for any sources of bias in our data collection. So we can make the sample as big as we want to try to reduce the margin of error to make it infinitesimally small. But if there's bias in your sample, doesn't matter. The margin of error can't make up for the bias. So given that, we want to talk about determining what sample size we should use. So in calculating the sample size for a desired margin of error when estimating the population proportion. So to determine the sample size n that will yield a C% confidence interval for population proportion P with maximum margin of error ME, we'll call ME the margin of error. Solve the following inequality. So you do your Z star critical value based on your confidence interval times the standard error here. That has to be less than or equal to your desired margin of error, and then you solve for n. So p hat is the guessed value for the sample proportion. The margin of error will always be less than or equal to the margin of error if you use p hat equals 0.5, just a rule of thumb there. Okay, so let's look at an example. Company has received complaints about its customer service. The manager intends to hire a consultant to carry out a survey of customers. Before contacting the consultant, the company president wants some idea of the sample size that will be required. One value of interest is the population P of customers who are satisfied with the company's customer service. The company president wants the estimate to be within 3 percentage points, or 0.03, at a 95% confidence level. How large a sample is needed? So we have no idea about the proportion P of satisfied customers. So we use P hat equals 0.5. This is going to yield the best result if you assume a 50%. Okay. Because the further away you get from 50%, whether it's higher or lower, when you do your 1 minus p hat, it's going to be the opposite. So if you say p hat's 0.75, then 1 minus p hat's going to be 0.25. But if you say p hat's 0.25, then 1 minus p hat's going to be 0.75. The kind of balance point is 0.5. If they don't give you if you don't have a p hat for your problem. Okay, we got to assume it's 0.5. All right, so we set up our proportion at a 95% confidence level. Our Z star critical value is 1.96. So using the equation that we talked about right here, this one, we would do Z star, so 1.96 square root 0.5 times 0.5 divided by the sample size. Now, we don't know the sample size. That's what we're trying to figure out. But we want the margin of error to be within 0.03, so that has to be less than or equal to 0.03. Okay? And now what we're going to do is solve this for n. The first thing, you got to divide by 1.96. And then you have square root 0.5 times 0.5 over n is less than or equal to 0.03 over 1.96. Then to undo the square root, we have to square both sides. So I'm not simplifying anything because we can type this all in the calculator at the end and get the most accurate answer. So you have 0.5 times 0.5 all over n is less than or equal to 0.03 divided by 1.96 quantity squared. Now, what we have to do is get n out of the denominator here. We can't just divide by the 0.5 and the 0.5 because the n's in the denominator. So we're going to multiply both sides by n. Okay, that will cancel these n's. And then we're going to divide both sides by the 0.03 over 1.96 squared. So I would have 0.5 times 0.5 over the quantity 0.03 over 1.96 squared, and that has to be less than or equal to n. Okay, so n has to be greater than or equal to essentially 1067.11. Okay, so if you read this inequality backwards, n has to be greater than 1 or equal to 1067.11. So since you're surveying people, um, you have to do a whole number. You don't round here. If you round down to 1067, you're not going to have enough because n has to be greater than or equal to 1067.11. So the sample needs to be at least 1068 customers. Okie doke. All right, guys, that's it for this section. We covered our learning targets here. Particularly in this video, we talked about how the sample size and confidence level affect the margin of error, and then determining the sample size required to obtain a confidence interval for a population proportion with a specified margin of error. All right, hope that was helpful to you guys. Reach out if you have questions, and take care.